Hi, I am Argha. So I will be presenting my work on implementation of mmWave-energy module and power saving schemes in ns-3. So let's get started. Since we all know, currently we are using 4th generation LTE cellular networks, and gradually we are heading towards 5th generation new radio cellular networks, which will be operating at millimeter wave frequencies. So these 5G new radio cellular networks are targeted to support diverse use cases such as enhanced mobile broadband, MMTC services, or ultra reliable low latency services. So energy efficiency is one of the key performance indicator for new radio technology. 3GPP in its 5G release 16 proposed various power saving schemes to operate 5G new radio with having very energy efficient techniques. So these power saving schemes are RRC inactive state and connected mode discontinuous reception mechanism, or CDRX. So in this work, we implemented user equipment RRC state based energy consumption model and also these power saving schemes, namely RRC inactive state and CDRX. So our module acts as a wrapper over the ns-3 mmWave module, which was developed by New York Wireless team and the University of Padova. So we have thoroughly evaluated our module and validated the implementation with the 3GPP standards. So earlier in 4G LTE, we used to have two different RRC states, namely RRC idle and RRC connected. So in RRC idle, the user equipment stays in less power consumption mode, or basically a deep sleep mode, where the context of the user equipment is not present at the base station. Gradually the user equipment gets connected to the base station and it enters in RRC connected state. So once the user equipment enters in RRC connected states, all its context or the mobility information, all that information is present with the network. So this switching from RRC connected to RRC idle or vice versa takes place with the help of a RRC inactivity timer. So the role of this inactivity timer is that suppose the user equipment is in RRC connected state. So in this particular state, the user equipment is receiving some amount of data from the base station, and suppose at a particular point of time the base station is not sending any data to the user equipment. So at that particular point of time, the user equipment will initiate its RRC inactivity timer, and gradually when this inactivity timer expires, the user equipment switches its state from RRC connected to RRC idle. So here we used to have a this timer basically leads to a trade-off between power consumption of the user equipment and communication efficiency. So if I have a longer RRC inactivity timer, in that case probably I am going to have a better battery life, but that might lead to a more latency in the communication performance. So to tackle this, 5G new radio going to incorporate a new state, RRC inactive state. So with this RRC inactive state, all the context of the user equipment is already registered with the network, or it is present with the network. The user equipment context, user equipment's identity or mobility information, everything is present with the network. And thus with this RRC inactive state, so this is also a less energy consumption state, but since the user equipment is registered, thus with compared to RRC idle, in this case we don't have much signaling overhead or control channel signaling overhead. And finally that leads to a better energy efficiency in RRC inactive state. And other than this RRC inactive state, we have another power saving scheme, which is CDRX. So in CDRX, RRC signaling sets a cycle where the receiver of the user equipment is operational for a certain period. So suppose initially the user equipment's receiver is turned on, or the user equipment is in RRC connected state, and the user equipment is receiving some amount of data. And once it stops receiving any data, in that case we have a smaller timer which is known as DRX inactivity timer. So this inactivity timer within its time window, it gradually checks if there is any paging occasion, or like there is any PDCCH reception happening at the user equipment. If it is happening, in that case the user equipment stays or continues in this connected state, or if it is not happening and if the timer, inactivity timer gets expired, in that case the user equipment enters in deep sleep mode. So, so finally, overall this DRX mechanism or CDRX mechanism, it helps in lowering down the net energy consumption of the user equipment. So the broad role of this CDRX timers is to call this or is to allow the user equipment to enter RRC inactive state periodically. Okay, so the contributions that we have made in our work. So we started working on top of this ns-3 mmWave module, which is publicly available as open source. So we started looking into it, and we found that there are certain implementation which we need to add for having a very energy efficient design. So the first thing that we have done is development of this RRC connection release method, which was not present earlier. And we also added this paging notifications to just to understand that if there is any PDCCH reception happening, or is there any uplink grant present at the user equipment. Additional, other than that, we also added this in RRC inactive state, this mechanism, and also implemented this CDRX mechanism, and finally we implemented RRC state based energy consumption model for the user equipment, which like this module helps in evaluating the UE's energy consumption across different RRC states. Okay, so that's the contributions that we have made. So the first contribution is RRC connection release method, which was not present in ns-3 earlier. So, so for implementing this RRC connection release method, we just have modified the LTE ENB RRC class and LTE EV RRC class. So in LTE ENB RRC, we have this function send RRC release. So this send RRC release, it will it comes from the ENB RRC, LTE ENB RRC, and it finally enters in LTE EV RRC class. Okay, and which finally helps in switching the user equipment state from connected to inactive. Okay, so that's the first contribution. And now for implementation of power saving schemes, the first is RRC inactive. So the first part was implementation of this RRC connection release. Now once I am able to implement this RRC connection release, the next state, the next function is to implement this RRC inactive state. So in RRC inactive state, the user equipment enters in this paging mode periodically. So what are this paging mode? It's basically a particular time window where the user equipment checks if it is receiving any kind of PDCCH or packet data control channel header data or notification, or like is there any uplink data grant from the inode B. So within this time window, it gradually checks if the notifications are coming. Okay, so that this periodic checking, we call it as paging event. So the paging direct message is sent to the user equipment from the inode B using this LTE ENB RRC. And finally, the LTE RRC SAP, it receives the paging information at the user equipment level, and finally it checks like whether this PDCCH reception notification is coming or not. Okay, so that's the role of this RRC inactive state. Okay, like so what if I receive this PDCCH? So in that case, our user equipment is going to change its RRC state from RRC inactive to RRC connected. Okay, and then again we are going to start our RRC inactivity timer, and if it expires, then again we are going to enter in RRC inactive state. Okay, and here I have a new timer, CDRX inactivity timer. So in this CDRX inactivity timer, I check if there is any PDCCH reception happening in this RRC inactive. If it is not happening, then our user equipment is going to switch its state from RRC inactive to a more power efficient mode, or the deep sleep mode, which we call as RRC idle. Okay, so so this diagram shows the entire flow of this RRC state switchings. So initially the user equipment is in idle state, and once it completes the RRC connection establishment, it enters in RRC connected mode. Okay, which is a high power state, keeping all the user equipment antenna turned on. And basically, like in this state, we are going to have a very active data transfer from the base station to user equipment. Now, like if my RRC inactivity timer expires in this state, or like there is no data transfer happening, and the RRC inactivity timer expires, in that case, our user equipment is going to change its state from RRC connected to RRC inactive. Okay, and in this RRC inactive, we are gradually going to check the paging events, and if there is no paging event and the CDRX inactivity timer expires, our user equipment is going to end up in RRC idle state, or the deep sleep state, where all the antenna of the user equipment is turned off. So that's the implementation of CDRX that we have done. And finally, the final implementation is RRC energy module. So for this RRC energy module, we have two components. The first is the energy source, and the second is the energy model. So the energy source is already implemented in ns-3, and we can easily install this energy source on top of the user equipment. So this energy source basically represents the battery of the user equipment. Okay, and now each user equipment is going to have a NIC card, or the network interface, or we can call it as a net device. So this net device consists of LTE VRRC class. So this LTE VRRC, it provides us the trace sources for RRC state switchings. And if I am going to have any state switching, in that case, this trace source coming from LTE VRRC going to fire a trace sync function, which finally helps in changing the power consumption according to the state of the RRC, and finally going to update the power consumption in the energy model, and in that way the total energy consumption of the user equipment is calculated, and the final energy calculated is sent to our energy source, which calculates the remaining energy of the battery life. And these are the power consumptions that we have made for different RRC states. Okay, so finally, for the evaluation of our implementation, we have taken three different kind of applications, namely file transfer protocol application, or FTP traffic, we have instant messaging application, and we have video streaming applications. So as you can see, like here we have a very two opposite application. One is instant messaging, where we are going to have the inter arrival time as 2 seconds, which is very long, right? So the amount of data coming at the user equipment for this instant messaging is very rare. But for video streaming, it's just the opposite thing, where for most of the time the user equipment is turned on and it is receiving a huge amount of data from some remote host. Right. So we have these 3 different applications, and like having different packet size or the inter-arrival times, and we have different CDRX timers. Right. We have different CDRX cycle length. We have different inactivity timer or the on duration in the CDRX cycle. Okay. So we have taken this different specifications as also proposed in the 3GPP specification release. And for the simulation scenario, we have one LTE base station which acts as the as a node which basically contributes in control channel monitoring part. And we have 2 mmWave base stations which act as the data forwarding part, and the user equipment which gets connected to one of the mmWave base station, and it starts moving at a speed of 5 meters per second from one base station to the other base station. And we have these 3 different applications. And also to compare the energy consumption of our model, we have taken 2 different baselines. The first one is the default ns-3 mmWave, where we don't have any RRC connection release implemented. So in the default one, what happens, if I start the simulation, the user equipment initially is in RRC idle, and once the connection establishment part is done, the user equipment enters in RRC connected, and it stays in this RRC connected for the rest of the simulation. And also I have another baseline, PHY state-based energy model. So this PHY state-based energy model is our earlier work, where we have this entire energy consumption model based on the PHY states. And this paper is from Infocom 2021 from the workshops. So so that's the evaluation setup we have made. And yeah, just to see the difference in these applications, as we can see here, for instant messaging, we can see for most of the time the user equipment is in connection DS or the deep sleep state or RRC idle state. But for video streaming, we can see most of the time the user equipment is in connected state, right? So that's the difference in the applications that we have taken. Now, we show the energy consumption and the average per packet latency for these 3 different applications under different CDRX timer settings. So as we can see here, for this instant messaging application, the first thing is that like if I don't add any CDRX mechanism, in that case the energy consumption is maximum, but the per packet latency is going to be very small, okay, since there is no switching off of the user equipment. But if I see under different CDRX settings, like if I keep a longer CDRX cycle, which is 320 milliseconds, in that case the net energy consumption of the user equipment is very low for instant messaging application, and also the latency is optimum. Okay, so that happens when the CDRX timer is longer, right? So since the inter-arrival time in instant messaging is very long, thus we can keep our user equipment turned off for a longer duration, right? Thus we have taken a longer CDRX cycle. Like thus if we keep a longer CDRX cycle, in that case instant messaging application will give you optimum energy consumption as well as optimum per packet latency. But for video streaming, since the user equipment is always turned on and there is active data transfer happening, thus in this case we need to keep the CDRX cycle of a shorter duration as observed in the evaluation. Like if I keep the CDRX cycle with a shorter cycle length, which is 40 milliseconds, in that case our user equipment consumes lesser energy as well as it performs optimally for from the perspective of per packet latency. Okay, finally we evaluated our module with the 2 baselines. The first one is RRC. The first one is the default ns-3 mmWave module, where there is no RRC connection release method implemented, which as we can see from this graph, which consumes the maximum amount of energy. And then we have another baseline, PHY state-based energy consumption model, where also we see that compared to our module, this PHY state-based energy model consumes a bit higher energy. That's because like once I implement this entire RRC connection release and the timers thing, in that case our application performs optimally. Okay, like if there is no inter-arrival of the packets, in that case I can I have that opportunity to turn off my antenna, or I can go to RRC inactive state, right? Thus our energy module performs optimally in terms of from the perspective of energy consumption. So in conclusion, this paper provides a detailed implementation of UE RRC energy model and the power saving schemes as defined in the 3GPP specification release. And we have thoroughly evaluated this module and validated the implementation from the perspective of 3GPP standards. And our results were compared with the baseline PHY state-based UE energy consumption model, and also that results show that our module performs better. So this module can help in designing energy-aware user applications as well as energy-aware networks that can provide a better user QoE and a longer battery life. And in our future work, we want to extend this module to support the base station energy modeling, so that an end-to-end energy consumption of the network can be captured. And finally, the source code of this entire implementation is available in this link. Okay, thank you. If you have any question, you can ask.